Thank you for your introduction, Martin. My name is Ian Wood. I am a Senior Application Engineer with CST of America, and I specialize in antenna simulation. And in particular, I focus on working with many of our mobile device customers. Today I'm going to be presenting our webinar covering simulation-enabled 5G antenna design. I'd like to just take a moment first off to thank the other contributors to the talk today, namely Konstantinos Prianidis and Matthias Gustafsson from Huawei Corporation, who have generously allowed us to share a concept study that they have been working on, as well as Brian Woods from our friends at Antenna Magus. So just very quickly, to start with, we will cover our agenda for today's presentation. We're going to open up and very quickly just discuss some of the basic motivation for looking at developing 5G technologies, as well as some of the challenges that the likely formation of these technologies will pose to antenna designers, as well as people using simulators such as CST. We're then going to get into a bit more focus on the available workflows that CST offers for antenna array simulation, as well as for multiple input and multiple output antenna systems. Both of these technologies are likely going to be pretty central to 5G deployment. Finally, we'll do this. The second half of the talk will cover a series of example workflows and studies. The first of these is a mobile device antenna array example. This will be followed by a MIMO base station demonstrator concept study that was put together by the contributors from Huawei. And then finally, we will cover very quickly a 5G Antenna Magus base station case study that was contributed from Antenna Magus. So of course, the fundamental motivation for developing fifth generation antenna cellular technology is to accommodate the ever-increasing bandwidth consumption that users of these devices are expecting. The precise increase rates vary a lot depending on the particular study you look at, but the consensus seems to be that within the next 5 to 10 years, our data requirements are going to increase by an order of magnitude. Not just because of the expectation for high performance, high speed communication on mobile devices, but also because an increasing number of devices are becoming connected and online in the so-called Internet of Things. This poses a challenge in particular when we look at deploying this technology, though, because what we could call historical cellular bands, those used by 4G or certainly 3G, typically are operating bands below 300 or 3 gigahertz. And this is, as a result, the commercial spectrum within this range is getting increasingly crowded. So much so that it's essentially been accepted that we'll need to look at a different spectrum allocation for these antennas. The current push from 5G research seems to be focusing on 28 gigahertz or higher frequencies for these antennas. Operating a commercial spectrum in this range will not only free up some of the spectrum resources, but also allow for faster data rates as well because of the bandwidth present. Unfortunately, this is not without its drawbacks and some fundamental challenges. Most importantly, once you start to get into these types of frequencies where you're really approaching millimeter wave class simulation or design, these types of radiating structures are subject to pretty high atmospheric attenuation. The path losses that you will expect operating in these frequencies are a lot higher than what we have become used to operating in the sub-3 gigahertz range. The change in frequency also has implications in the behavior in the operating environment as well. The smaller wavelength means that the physical operating environments in an urban environment or wherever the user may be has become electrically larger. And as a result of this, they're typically more susceptible to multipath loss in these types of systems. So if we look at how one would approach tackling this from an antenna perspective, what becomes abundantly clear is that because of these high losses that are present, because of the high attenuation, the efficiency of the antennas is very, very critical. Typically, gain targets of about 12 dB are what we would shoot for the mobile devices for this category. And then, of course, on the base station side, you can expect a bit more gain because of the extra real estate. 25 dB is the typical target we're seeing there. For mobile devices, though, gain presents something of a double-edged sword. Obviously, it's increasing the efficiency of your device, but it also adds directivity inherently to the equation as well. And this is not necessarily a good thing for a mobile device. Obviously, our users will need to be able to maintain a high-speed data connection regardless of the relative orientation of their device to the parent base station. So typically what antenna engineers for mobile devices shoot for are relatively omnidirectional patterns, such as the one that you can see in this slide in the lower left-hand corner for just a simple PIFA antenna that would be typically employed in legacy cellular systems. The solution to this that will allow us to leverage high gain and high efficiency while maintaining coverage is beam-steered arrays. These give you the mobility to adjust the peak amplitude or the direction of your main lobe of the antenna by phasing the excitations in your array while maintaining the high gain that's typical of such an array. Another way that we can leverage antenna design to increase the efficiency is by taking advantage of diversity gain, namely by using multiple input, multiple output antennas as well. Of course, all of these trends do pose a challenge for the simulation perspective as well. The higher frequency fundamentally means that because of the basic spatial sampling requirements that you need to honor to accurately model propagation in 3D, it means that you're going to require more mesh cells for a given size structure as you increase the frequency or decrease the wavelength. So the number of cells to simulate what are typical physical size mobile devices or base stations becomes quite a bit more challenging in terms of the memory footprint. So high efficiency solvers are very, very valuable in these situations. So clearly, arrays are a very central technological tenet for 5G technologies. So we're going to focus a little bit more on the different options on how we can tackle those within CST Microwave Studio. And broadly speaking, the workflow that we recommend can be categorized according to the array scale. Namely, we would categorize arrays according to being a large array, such as the one you would see on the left here, or a small or finite array, such as the one you see on the right in this slide. The key factor that differentiates these two is the relative weighting of the edge elements. In the case of a large array, the majority of the radiating elements are internal elements that have the full unit cell of adjacent neighboring elements. And this means that you can very, very accurately and safely opt for a unit cell-based periodic approach in which you would really only model one of these elements in 3D with some type of periodic boundary, and then apply an array factor to the resulting element pattern to obtain a nice representation of the overall array performance. In contrast to this, for what we would call a small array, the relative contribution of the edge elements is much higher. So neglecting the change in their individual radiation patterns that this causes will result in generally fairly inaccurate array level performance. Hence, you really do need to solve the whole finite array in a single 3D model. Of course, when we talk about mobile devices, form factor is paramount in modern devices. So obviously the types of arrays we would be looking for on this side would very clearly fall under the small array category. Historically, base stations would be more along the lines of something that we would talk about as a large array. But one of the implications of the higher path loss, in addition to having higher efficiency antennas, is a decrease in cell size for the cellular network, which is making more compact base stations increasingly attractive. So they may also exist in something of a gray area between these two categories. So of course we'll focus first more then on small arrays because this is definitely the most pertinent workflow for 5G antenna simulation. So in this case, we cannot do a periodic approach, so each element will need to be simulated. Depending on the operating specifics such as bandwidth, the overall electrical size, any of our flagship general purpose solvers are well suited for this type of simulation. However, particularly at higher frequencies and for larger finite arrays, the very, very low memory footprint of the time domain solver can become highly advantageous, and it's generally the one that we suggest for finite array simulation as a result. There are two different approaches in terms of how we can achieve the excitation of this array. The most obvious, of course, is to individually excite each port and obtain a full S matrix. This is obviously quite flexible because then we can experiment with different beam weightings in a post-processing capacity. The downside to this approach, at least from the perspective of a transient analysis, is that this would necessitate that each of the ports are excited and simulated in series, which gives you an n times linear increase to the overall simulation time. Alternatively, if you are relatively certain of the number of beam or amplitude weight combinations that you're interested in examining, then you can also have the option of simultaneously exciting the array. So in this case, all of the elements are actively excited at the same time in 3D. This, of course, will not give you meaningful S parameters because this is not the condition under which S parameters are defined, but it only requires one 3D pass. Of course, if you do opt for the full S matrix option where you would excite all the ports in series, there are, of course, some performance computing options. In particular, our distributed computing capability can be very attractive to mitigate that disadvantage that you have when doing a transient analysis. In particular, you can use distributed computing to set out the ports to be solved in parallel on different compute nodes in a cluster, giving you a linear increase to compensate for the extra time it takes to excite those ports. This extra work will really pay off if you're looking at either doing a lot of optimization iterations on your overall beam weighting, or if there are just a rather lot of different combinations that you're interested in studying. Particularly if it's likely that the number of perturbations of your amplitude and phase weights exceeds the number of ports by a large margin, then this is an indication that you should use the S matrix approach and excite all of the ports so that you can combine the results and obtain the array pattern via post-processing, which is obviously much, much quicker than doing a full 3D simulation. Here's a nice example of how you could leverage this approach. In this case, we have a finite array in which all of the amplitudes are initially set to 1 and a full S matrix is generated. And then we can run an optimization process to adjust the amplitude weights of our different ports to make the resulting array beam shape conform to the desired beam shape. And what's particularly nice, as you can see in this slide here, is that the optimizer within CST can opt for an entirely template-based post-processing type optimization. So this means that each optimization iteration is just doing the superposition post-processing to combine to ports according to the weight that you have specified here. So very, very quick compared to actually re-solving in 3D for each amplitude weight. Of course, we also have some very nice capabilities to realize your amplitude weighting and feeding network once you have finalized on a design. In particular, Design Studio, our system and circuit level solver, provides a nice scalable level of detail in designing a feeding network, such as the one you can see on this slide. In particular, you could start off with ideal elements, perfect phase shifters, ideal transmission line models, phase that up to one-dimensional models, for instance, or planar models that are also supported for transmission lines in Design Studio. And then finally, you can also use this as the basis to assemble a full 3D structure for final validation as well. Just a quick note, for large arrays, as we mentioned, it's relatively safe to approximate the unit pattern as an infinite array. So you would just pick a single internal element and set either periodic or unit cell boundaries depending on the angle of periodicity. And this will take into account the coupling effect that occurs for internal elements to their neighbors on all sides. After you've obtained this element pattern, you can apply an array factor that includes the overall array dimensions and the spacing between elements to get a very, very nice approximation of the large array performance. Here you can see this general trend as you increase the size of an array, how it begins to converge onto this unit cell approach. Here you can see a unit cell with a element pattern here in contrast to element patterns for larger and larger array sizes. And as you can see, as the number of elements is increased, the accuracy of the unit cell approximation increases as well. Although obviously as you approach plus minus 90 degrees, there are some fundamental limitations because of the periodic boundaries. Finally, we'll just end our array discussion with a little bit of a preview of some of the nice new features that we're introducing in our 2015 release that will be coming early next year, that in particular have added some nice interface features to aid array designers in rapidly constructing either large or small arrays. In particular, we now have our CST Array Wizard, which can construct finite or unit cell arrays as a simulation project within Design Studio. So here you can see just a quick screenshot of an example dialog. We'll actually be showing this wizard in our first example as well for some more detail. But essentially, you specify the number of elements, the spacing between said elements, as well as the option to have an angle in your array grid, as well as specify an amplitude distribution. Once this is done, all you need to do is just drop in your version of your element model, and then create either a unit cell or a full array simulation project, depending on whether you're opting for a large or small array analyses respectively. Once this is set up, another nice capability is that you can toggle individual elements in the overall array to either be active, passive, or to be empty as well, which is quite nice for inhomogeneous arrays. And here you can finally see if you were to create a full finite array project, you'll get a nice full 3D representation of the finite array, which is obviously the most applicable to today's conversation. And again, we will show this in our first example. It will also be, of course, well covered in our coming 2015 update webinars that will cover all of the new features that we're introducing in the new release. So I would definitely encourage folks interested to keep their eyes open for that update webinar as well. So with some picture about the array capabilities and workflow within CST, now let's just talk very, very briefly about multiple input, multiple output antennas. So of course, if we look at your typical communication channel in a typical urban environment or even a rural environment, what becomes pretty clear quite quickly in the context of cellular usage is that the environment is going to cause a lot of reflected paths between the user and whatever base station they're in contact with. And the slight delay in transit times that these different paths have, because they have different path lengths, this can mean that the received signals have the potential to interfere deconstructively with one another and cause a dip in the received signal and potentially a dropped call or a loss of data signal. Of course, that's just a path consideration, but there's also polarization decay rates as well that can individually be accounted for in models as well. The way to combat this type of fading that can occur, what's called multipath or rally fading from these multiple paths, is to introduce diversity into your antenna design. This is the so-called multiple input, multiple output antennas. So you can see here just a very, very simple MIMO antenna where there's a bit of spatial diversity as well as a polarization shift for these pair of PIFA antennas. And you can see in the resulting received signal, because we have these two relatively decorrelated signals, when one antenna is subject to a fairly large path fading dip, the other antenna is not, because it has low correlation. And as a result, the signal that we actually receive, we can opt between the best of the pair, and we get an effective gain from this diversity. We, of course, this is a fairly established design approach within antennas, perhaps not so much in the mobile space, but we, of course, have post-processing options pre-implemented into the software to give you very convenient access to all of the pertinent MIMO quantities. Obviously, diversity gain is probably the most common, but the envelope correlation coefficients that this is derived from are also available, in addition to multiplexing efficiency or mean effective gain if you're just looking for your single element performance as well. There is also a webinar available from last year that covers MIMO antenna simulation in detail and is available online. Okay, so enough establishing theory. Let's now move on with our series of workflow examples. So as mentioned, the first example we will look at today is that of a mobile antenna array. So we are going to start off by designing the array element, our antenna that we'll use as the element for this array. We're then going to design the array itself for a specification based on gain that we expect to see based on or want to see based on the 5G specifications. And then we're going to look at this array performance both in isolation, but also we're going to look at how its presence when it's installed in the actual mobile device, at a device level, how this influences the performance and how we can potentially compensate for that. And then finally, we'll go up to what we would call a system level performance analyses as well, and add in a biological model of a homogeneous human hand to see how this impacts our antenna performance as well. For those of you who have attended a few of our webinars in the past, the mobile device may look somewhat familiar. In particular, our array here is in the top left-hand corner. You can see a cluster of discrete ports. But we're also going to examine how this couples to some existing antennas that we have installed in the mobile phone. In particular, there's a Wi-Fi antenna you can see to the right-hand side of the phone, a GPS antenna in the main screen of the phone, or below on the PCB rather, and then finally a hexaband antenna at the base of the phone that supports legacy cellular. So starting off, we are going to design our antenna element. And to do this, we can take advantage of the nice Antenna Magus product. Antenna Magus, for those of you who may not be familiar with the tool, is essentially, it's a large searchable database of antenna designs. You can see here just a screenshot from one of the more recent versions of Antenna Magus. It's now over 250 elements to choose from. And each of these elements has design synthesis built into it so that you can actually automatically generate an initial design for your performance specifications. I think the value of this tool is really, really evident to newer antenna engineers because it gives them a very, very nice consolidated information source, as well as a nice list of candidates of antenna design or antenna topologies that are likely appropriate for them. But maybe more to the context of 5G antenna designers, I think Magus also poses a lot of value for engineers who may be very experienced with a certain antenna category and a certain operating frequency in this case, but maybe looking at designing a device with quite different design specifications and might warrant looking at topologies that the engineer might be less familiar with. And Magus is certainly an excellent way to kickstart or make that process a little less daunting. So in this case, we opt for a simple rectangular patch antenna, square patch antenna with a simple pin feed. You can see we've designed it in Antenna Magus synthesis design tool for an operating frequency of 28 gigahertz. We've specified a 50 ohm port impedance and a relatively generic substrate. The synthesis objectives are, of course, quite flexible as well. If you weren't concerned with a specific substrate, you can leave that as a default and just let Magus choose one for you. Similarly, there are default impedance options available as well. So you can see that the initial design that Magus has suggested here towards the right with the parameter values and the relevant design spec. Within Antenna Magus, there is also a performance estimation tool. Now, estimation is a key term here. This obviously does not have the accuracy of a full 3D simulation like that you would obtain in CST, but what it can provide you is a very, very quick indication of how close this initial design is going to satisfy your specifications. So you can see here that in this case we are indeed quite close. In particular, if you look at the reflection coefficient, we're a little bit detuned. At this high frequency, the design models, it's challenged to get these standardized designs. So it's a little bit detuned. It's something we will likely want to address when we bring it into the 3D tool. More importantly, though, we see we're in pretty good shape already just from the element if we look at our radiation pattern. We're at about 7.5 dB element gain. Recall that what we want to shoot for is around 12 dB in the array, so we're expecting on the order of around 5 dB gain from the array factor, which should be quite doable even for a modestly sized array that will accommodate the form factor. So of course, we can export this model into CST Microwave Studio. The model that you will get is pre-validated, so it's really ready to just launch. It's accurate. It's all set up for you. And it's also pre-parameterized for you, which is particularly nice, as you'll see here. You can see that when we run the full 3D simulation, the performance is slightly more pessimistic in terms of the S11 performance than what we saw in Magus. We're closer to 26 gigahertz in tuning. But we're actually a little better off. We're closer to 8 dB in terms of overall gain from the device, so it's a bit of a wash. Of course, we can use CST's simulation and optimization capabilities to improve our performance. And we can also leverage the information that Magus provides us. In addition to this design synthesis, each of the antenna elements that you can choose within the Magus database is very nicely and thoroughly documented. And in particular, there's these nice design guideline summaries provided for each element that provide you with a general summary of the design trends and constraints that you have to work with. So you can see the first note that it makes here is that in order to increase the resonant frequency, we decrease the patch length, which of course for a patch antenna this is relatively self-explanatory. So we activate our patch length parameter within Microwave Studio for optimization, and then we just simply specify an optimization target where we would move our minimum in the S11 to be at our operating 28 gigahertz frequency specification. You can see here the result of the optimization, although we can also see why Magus likely opted for the solution that it did. While we have a superior tuning now at 28 gigahertz, the peak quality of the impedance match has been somewhat degraded, something that might be needed to be compensated for in a matching network. As we'll see, though, it would probably make sense to investigate that discussion perhaps further down the design process once we've accounted for mutual coupling or perhaps the detuning effects of the installed environment that this will be operating in. The picture is, again, a little better, even more so now that we've adjusted the patch length. This change in the aperture dimension has actually been fortuitous for us, resulting in an increase in gain to be over 8 dB now, a slight improvement. So with our element finalized, we would now look at doing our array design. And thankfully, Antenna Magus actually has some very nice array synthesis tools that we can leverage to expedite this process and get a very, very good workable initial design, exactly as we did for the antenna. So you can see on the left-hand side of this slide a small selection of some of the array topologies that Magus can work with. Obviously simple linear arrays or the planar array type that we'll be working with today, but also more complicated situations such as concentric rings or cylindrical arrays are supported as well. In this case, we are actually going to be steering the array dynamically within CST itself once we export to Microwave Studio. So rather than opting to design for a particular steering angle, we're just going to get Magus to synthesize an array for us based off of a gain target. And in this case, we're going to shoot for around 8 dB gain from the array itself. You can see here the resulting matrix layout, the distribution matrix that Magus suggests for this in the top left-hand side of this slide. It's suggesting a 3x3 array, which should be very workable for the form factor that we were looking to use in our mobile device. In the case of isotropic radiators, you can see the derived array pattern that will occur has around 10 dB gain. It's just immediately to the right of the distribution matrix layout towards the center top of the slide. Of course, in our case, we don't have isotropic radiators. We have a fairly directive rectangular patch antenna already. So we can actually specify a specific element pattern for use in this array synthesis. You can see in the lower left-hand side here a listing of some of the more canonical generic radiation pattern types, such as an ideal cosine Q directive pattern, for instance. But we also have the option of importing an actual radiation pattern if we have a finalized element, as we do in this case. So we can just import our actual element pattern that was obtained for the square patch antenna. And you can see Magus is predicting quite a nice peak gain, around 14.5 dB at least at bore site. So this also shares a similar link between Antenna Magus and Microwave Studio. We can export this distribution matrix either as a wavelength-based matrix or as a physical-based matrix into CST, and then key this into our array wizard to use this as a basis to construct a finite array. Instead of doing this approach off screen, so to speak, we'll take this opportunity to show how you might set up this array using our new phased array simulation project that we mentioned as part of the new CST array wizard. So what we would do is simply switch over to our schematic tab within Microwave Studio. You can see here our element within Design Studio. And then we would create a new phased array antenna simulation project, which would bring up the properties for that task, in which case we would specify a 3x3 element array with the spacing that Magus dictated and no grid angle. From this, we then create a full array simulation project, and of course all of our elements are active, obviously in an array this scale. And this is going to automatically create a full finite 3D model. You can see the geometry with overlaid surface currents that result here from a boresight excitation on this finite array. You can see that we are seeing similarly promising performance in the boresight, the 90-degree radiation pattern here when this isn't being steered at all. If we look at the resulting S matrix, we see that indeed neighboring elements are causing some additional detuning here. We see our null has increased in frequency somewhat, so you can understand that if we were to match this, this might be a more appropriate opportunity to do so either in Design Studio or with other products. Of course, the performance on boresight is probably the best case for the gain that we're going to get from this array. As we look at how this array performs as we steer the main beam location to other locations, we want to understand the overall coverage pattern that we could expect to obtain from steering this array as we adjust the beam direction as the mobile device shifts. To give a nice understanding of this capability, we've added a very cool new feature in our far-field result post-processing template. And this has come out of requests from a lot of our user base who are involved in developing 5G antenna systems already. Namely, what we've added is what we call our best achievable pattern envelope. This is just available as another result value within the far-field result template that I'm sure many of our attendees are familiar with already. And what this does is it's going to record the resulting far-field pattern as we look at different steering angles. So for instance, on our array here you can see on top our familiar boresight firing configuration where theta and phi both equal 0 degrees. If we were to steer this such that we were 15 degrees away from boresight in elevation and 30 degrees azimuthally, you can see there's definitely some pretty big changes in the resulting radiation pattern. What the best achievable pattern gives us is the overlay of both of these patterns. Now obviously we'll be sweeping a lot more than just a single direction in our analyses, but hopefully this gives a clear indication of what this is outputting. And certainly it gives a very nice intuitive level of insight to the array designer in terms of the coverage that they're getting to just visually inspect this and see how their gain really is going to perform over these different angles. So here you can see for a sweep of steering angles what our array performance really looks like. You can see in the top right-hand corner, obviously for shallower steering angles, in this case this is a pattern for theta equals 10, so we're just 10 degrees off boresight, and then the full 360-degree azimuth sweep. So you have the full circular range. And you can see that obviously for the smaller scan angles, this is pretty okay. As you get up to theta equals 45 degrees, though, we start to see some interesting trends in the steered array. In particular, we get some nulls here on the sides, the horizontal sides of the array where we have some blindness. This is something that we could look at tackling potentially by adding a token amount of diversity to our antenna design, perhaps by rotating a secondary array within the device. It's also worth noting when we're looking at these swept patterns that clearly this is a hemispherical array. These square patch antennas operate off of a ground plane. This is really only giving you the plus minus 180 degree, or the top hemisphere of your spherical radiation pattern. So in the eventual device, we'll need a pair of these, one on top and one on bottom, to get the full spherical coverage that we want from our device. If we look at a single azimuthal angle to get a so-called sort of a cut of this performance, we can see that really we're only hitting our 12 dB target out to about 60 degrees in this case before we're degrading below that gain. Although even right at 90 degrees, where this substrate is practically end firing off of the edges, or perhaps there's some diffraction effects there from the edges, we're actually not too bad off. We're still getting around 4 dB gain there, right to the edges of this design, which is pretty promising. That, of course, is the array operating in isolation. This is going to be installed in an actual mobile device eventually, and we need to understand how that device's presence is going to impact the performance of the array. Of course, anyone familiar with the Microwave Studio build tool knows that there's a lot of ways to assemble these types of projects, either directly in 3D or merging multiple sub-projects. I think particularly in this case, when you're bringing in perhaps multiple instances of antennas or antenna arrays, a particularly attractive option to construct this is our system assembly modeling. And this is something that we set up in our schematic view, similar to how we worked with our array wizard. So here you can see Microwave Studio model schematics have been dropped into the canvas. In the middle here, unfortunately a bit small, is our mobile device, and we'll see that in more detail in the subsequent slides, as well as two instances of our 3x3 finite array that we've just designed. So again, one for the top of the device and one for the bottom. But what's particularly nice, as you can see, is that when you're using this approach, each of these array instances have their own independent set of parameters. So if we did need to, for instance, compensate for the tuning of the device according to its installed performance, we could independently tune the top side and the bottom side arrays in this case to get the best performance for both operating conditions. Similarly, even if you were perhaps using system assembly modeling to build your array, this is one approach that you could use to very quickly generate an inhomogeneous array with parametric control individually for each element. Now, because we're going to be aligning these things, we're basically mounting them structurally. There's no electrical connection beyond those we'll form with 3D placement. All we need to do is just wire in external Design Studio ports to each of the wire terminals on these Microwave Studio blocks to make the system complete. After we have our design canvas taken care of, we need to define the relative alignment, how these different 3D models that we're bringing in are oriented to one another. To do this, we can go into the Layout tool, which will bring up a 3D modeler window very consistent with what you're used to in Microwave Studio that allows you to then align your different geometries together such that they reflect the installed performance. So here you can see how we would go about this for our so-called top array on the upper side of this device. And in this case, we can just simply do a transform command, even using pix, to move this from the center of the original coordinate system to its first intended location towards the upper left hand of the device. For the bottom side array, we do need to do some additional layout work. We would need to first rotate, flip the array on its face so that it's now facing downwards, such that its bore site is now in the negative z direction. But as mentioned, we'll also rotate it 90 degrees about this axis to introduce some diversity into the design because of those nulls we saw at 45 degrees. Once this is done and the relative layout has been defined, we then create a new simulation project. The simulation project at a fundamental level can be any combination of what we would call schematic or circuit blocks and 3D blocks. In this case, though, obviously all of our structures are 3D, and we want them to all occupy the same 3D simulation that we're setting up. This is, of course, a relatively common scenario, so it's available directly in the simulation project menu. You see we can just directly specify that all blocks be handled as a 3D model. In the resulting simulation project dialog, we just simply specify this is a Microwave Studio model. It's using the transient solver, and we even have the option of referencing one of the blocks for all of the EM settings. In particular, we're interested in the array performance here, so we've opted to use the EM settings for our patch array. On the right-hand side of this slide, you can see the finalized full 3D model, complete with all of the ports being placed and ready to have a full 3D simulation that will cover all of the interactions and installed performance. So now that we've put this thing in our generic smartphone, with some other realistic antennas present here, this is definitely getting to a point in complexity where it's perhaps something we could call realistic. It's at least approaching this. Because of the extra complexity and the extra simulation space, recall we are solving this at 28 gigahertz, so it's a lot higher frequency than what you would typically solve a mobile device at like this at currently. This is just over 10 million hexahedral mesh cells, which sounds like a lot, but particularly if you can take advantage of GPU computing to accelerate this process, it's really not a particularly lengthy simulation at all. On a fairly high-end dual CPU workstation with an NVIDIA Kepler 20 GPU, this only takes about 3.5 minutes to solve per excitation, so hardly enough time to even get yourself a cup of coffee. Additionally, this is only taking up about 10% of the GPU capacity, so you can take advantage of that speed up for much, much more larger and complex models than this one. Perhaps even more encouragingly, as I noted, because of this shift to a frequency and order of magnitude higher, the memory footprint of these devices is going to be very, very important. And you can see that in this case, the time domain's memory footprint is very, very minimal indeed. At under 4 gigabytes of system memory in terms of capacity, this is the type of simulation you could very easily do on even a mid-range laptop, let alone a workstation. Here you can see the resulting coupling information to the other antennas. You can see this resulting surface currents and animation on the right-hand slide here, as well as what we call the F parameters, or the coupling, the frequency parameters that represent the coupling to the Wi-Fi, the GPS, and the hexaband antenna when we are illuminating our arrays with simultaneous excitations in bore sight. So because these are firing just straight up and down, this is something of a best case scenario potentially for the coupling, whereas if we aim the array towards one of these devices, we might even see further performance degradation. Right away, though, we can see that even our bore sight gain has been decreased in installed performance. It's now only 11 dB of gain. But more importantly, if we look at our coupling information, we can see that there's a fair bit of in-band coupling occurring to, in this case, our Wi-Fi antenna, port 21. And this makes a lot of sense if you look at the spatial relationship between the bottom side array and the Wi-Fi antenna here. What's also interesting is that even though the coupling level is a little bit lower, if we look at our GPS antenna and plotted in green here, you can see that there is some coupling in the 5G band at 28 gigahertz. And this actually is somewhat visible on our surface current plot here. You can see that on the far side of the GPS antenna, there's some blockage occurring there. So we want to make sure that we examine the effects of that on the radiation pattern. If we want to better understand the coupling, the methods of coupling, we can individually excite the two arrays as well as steer them to understand which is the dominant coupler. As one would expect, as you can see from the cross-section here, the lower array is the dominant culprit for our Wi-Fi coupling. It's fairly obvious to see why this is the case when you look at a cut of the E fields, which you can see in the lower left-hand corner of this screen. You can see our array strongly radiating on the right-hand side, and then some of that energy is directly blasting into our conformal Wi-Fi antenna seen on the right-hand side of the picture. If we look at the envelope, before we go on, just as an aside, for those of you interested in this type of analyses in terms of allowing for the coexistence of antennas, we do have a nice webinar that's available already for this that you can see in this slide. So if you're interested in more in-depth discussion of that type of analyses, I'd encourage you to check that out. Moving on, though, let's look at how the installation has affected our best achievable pattern envelope. So you can see on the right-hand side, or sorry, on the left-hand side rather, our performance at theta equals 85 degrees for the array operating in isolation. And you can see when we do the same thing when the array is installed on the phone, we can see that indeed the GPS antenna, as we suspected looking at those surface currents, is indeed causing a fair bit of blockage in that direction on the top side antenna. We can see that in the direction towards the bottom of the phone, there's some substantial degradation in our performance. So we might want to look at either getting some sort of isolation between the GPS antenna, or perhaps looking at a different element entirely to mitigate this effect. Finally, let's scale up the complexity even further and add in biological models. So of course, historically, the primary focus of introducing biological models into your mobile device simulation was primarily for certification purposes. Of course, the FCC and other international standard committees have very strict regulations on the allowable SAR or the amounts of radiated power that these devices can radiate while still being deemed safe for use by the general public. Additionally, there have certainly been some cases where we've seen the need to include these biological models in close proximity to the antenna to also understand the antenna performance. And because of the increase in frequency that we're using to go to 5G, as well as the fact that the standards are likely going to need to be reformed as we switch to these higher frequencies, this is the dominant focus, the antenna impact for our discussion today. A nice thing we added last year in CST 2014, I believe, was we added a number of CTIA standard hand models to our installation help files that are available for our user base to work with for exactly these types of simulations. These are available at preset angles, as you can see here in the middle of the slide, but also as an entirely posable parametric model. So in this case, you can see the parameter list that I generally use for this class of 4.5-inch smartphone device, which is becoming increasingly standard. Obviously, your mileage will vary for these particular parameters. The nice thing, of course, is because we opted to use system assembly modeling when generating our installed performance model, it's very, very easy for us to scale in extra system complexity now. All we need to do is just drop in our posable hand model with the spacer included, and then redo our layout. We don't need to bring in anything else. And the layout, of course, it's very, very intuitive. As you can see, these hands do come with the spacers included. So you can literally just slide the phone model onto the spacer tabs exactly as you would if you were working with this in the lab. You can see here the resulting 3D model in wireframe with the hand included. Obviously, the extra simulation volume as well as the material properties in the hand substantially increase the mesh count, in this case to just shy of about 30 million cells. This is definitely getting into what we could call coffee break duration workstation per excitation. It takes just about 15 minutes on that same dual CPU workstation, and we are making the GPU sweat a bit more at 35% capacity at this case. But clearly a ton of room to grow still in terms of capacity and time. The memory usage is also increased, but we're still under 10 gigabytes for this model, which is quite nice. Particularly if you started to include a homogeneous head model, which is much larger if you were to do SAR, you can imagine how high the mesh cell count could get very quickly at these frequencies, and that memory footprint is going to become a very, very nice feature indeed. So if we look at the effects of the presence of the hand model, as one would expect, because we have a fairly directive device, our top hemisphere array is largely unaffected. In contrast to that, though, if we look at the bottom array, and as you can see here in the picture, our selection of a location for the array is problematic here because this user's index finger is almost entirely blocking it. In fact, if you look at the resulting radiation pattern, you can almost see the interference pattern that the fingers are individually introducing here. So clearly, probably not a good location for our bottom side array. It would need to be moved perhaps closer to the edge of the device. But more importantly, hopefully this speaks to the necessity of including these types of models in your design for these types of devices. That concludes our mobile device example. We'll now go ahead with our base station examples to tell the story at the other end of the communication channels. And the first of these is a very nice MIMO base station concept study that some of our users at Huawei have generously allowed us to share with you today. This in particular was a concept study done for MIMO base station array design that was part of a thesis project done at the Chalmers University of Technology in Sweden. For those of you interested in more detail, there's the full reference available here. So as I mentioned, this is just a concept study for the moment. It's a novel antenna array that essentially looks at ways that we can increase the capacity and efficiency for small cell sizes while maintaining a small form factor so that this can be placed in discrete locations, but also maintaining a very nice 25% bandwidth. This design was done more at legacy frequencies, centered more around 2 gigahertz. But a lot of the concepts here, when it's speaking to a small cell size and it's using MIMO, this definitely speaks to what we expect to see in 5G, as well as to some of the intermediary technologies that I think we'll see even sooner as we try and increase the capacity of existing 4G. So the MIMO diversity gain that this design uses is really central to the improved efficiency. There are 2 logical ports in this design, essentially corresponding to the different polarizations that this array can independently receive. In particular, there are elements that exclusively receive the horizontal polarized electric fields as well as the vertical polarized electric fields to give you a very nice level of polarization diversity. Similarly, inherent to this type of array design, especially when you look at a relatively exotic layout like this, there's also spatial diversity inherent to this. And there are, of course, 12 physical ports that you can leverage for this capacity. Depending on the phase arrangement, though, this resulting performance, as we'll see, can actually result in some very nice steering capabilities. In particular, it has a full 360-degree azimuthal plane beamforming capability, as well as full up-down tilt beaming capabilities as well. So very flexible and highly efficient. So it can definitely speak to these small cell sizes quite well. If we look at the horizontal element design, this was essentially designed as a loop antenna, which is a fairly strongly horizontally polarized element. Loop antennas are generally fairly unpopular, particularly in these applications because they're quite large, however. So to make the design more compact, the authors here very cleverly used a set of 4 printed arc dipoles that are centrally fed by a coaxial feed line. Now they've compensated for the size somewhat, but in order to increase the bandwidth, they also have added a parasitic tuning element with these tapers here that provide a nice transition between the feed and the radiating elements. You can see here the resulting radiation pattern is very, very nicely horizontally polarized. You can see the pattern for the horizontal pole on top, and then on bottom much, much lower, so well over 11 dB of discrimination in this case. A very, very nice horizontal element. The vertical elements were designed sort of like dipoles, although as we'll see, they're present on a small ground plane, so it's more realistic to say that they are small ground monopoles. You can, of course, increase the bandwidth of these by adding a planar width. So these are actually patch antennas. And you can see similarly this has a very nice degree of discrimination as well between the vertical on top in this case and horizontal on the bottom radiation patterns. You can see here that they were able to obtain a very nice wideband performance with these techniques, which is quite nice given the compact factor of these elements. Unfortunately, the horizontal elements, even though they managed to shrink them down quite a bit for the physical form factor, of course the phase distance between elements is or the wavelength distance is also highly important for the array performance. And in this case, it was still slightly too far spread out from each other for the case of the horizontal elements. So quite a clever solution that they opted for in this case was to actually add finite ground planes on top and bottom in the mounting structure. You can see these are the top and bottom circles on the physical array you can see pictured to the right here. And what these do is they add a reflected signal. And the distance to the horizontal elements to the top and bottom ground planes was selected such that these reflected signals interfere with the grading lobes that have been introduced by our non-ideal spacing. It also provides the ground plane for our vertical elements as well. So this means that the array can either be operated omnidirectionally by exciting all of the elements uniformly, or you can also steer the array by adding phased relationships between the horizontal or vertical elements internally. Finally, we're going to look at a mobile broadband communication system that is a bit higher frequency, operating at the 28 gigahertz system. But in particular, we're going to show how you could use antenna magus to do some exploration, some design exploration, in terms of what types of antennas you might want to investigate further. So in particular, we're going to really quickly examine two different options for implementing this base station. In particular, we'll look at a sectoral array of reflector horn antennas. So we'll rely on a single element to obtain our high gain. And then we'll compare how this performs to an array of waveguide-fed horn antennas or waveguide antennas that are also arranged sectorally to see how they compare in terms of performance. So of course, the first option we have here, the single horn antenna, this is very quick to design using the Magus synthesis, and we see we get quite good gain performance very quickly, along with the physical derived dimensions that we will compare for compactness. And you can see here, if we arrange these in a hexagonal layout, we get a reasonable sectoral coverage with nice gain. If we compare this to what we obtain with our waveguide antenna-based array, we create at first our individual element, and in particular of note here we see that the waveguide height of our element is just shy of about 7 millimeters here. When we try and build an array to get our target gain to increase this, what we find though is that Magus suggests a spacing between elements that is smaller than the physical height of the waveguide, which is obviously not realizable. So we need to adjust the synthesis objectives, and fortunately, as we saw, there's a lot of flexibility in terms of the types of inputs that we input to the specification. So in particular, we can read over the number of elements as well as the number of elements that we get from the suggested synthesized array, and use that as an input in the objectives for our new array, but also directly specify a spacing that's realizable. So what we see is that we can still obtain a good level of gain comparable to before with that wider spacing, but we just need a slightly longer array. We're looking at about 9 centimeters overall versus about 7 centimeters for the original array specification. And similarly, if we arrange these in a sectoral arrangement, we can see there's reasonable coverage here as well. More importantly, though, we see when we actually look at the resulting form factor, our arrangement of horn antenna arrays is providing us with the required gain and coverage with a much smaller form factor, particularly in terms of the width, compared to the sectoral horn antennas. So this likely makes it a much more attractive candidate for subsequent in detail study for the design. So in summary, we've just shown how some of the design requirements for 5G, how this is pushing towards higher efficiency beam steered array designs. We've shown the CST array simulation workflows and system assembly modeling that can speak to this design flow and expedite that process for engineers. As well as we've shown Antenna Magus's capabilities in providing antenna and array synthesis, as well as some of its abilities for rapid design exploration. And finally, hopefully we've driven home the importance of these types of system-level simulations for antenna performance, especially at these new 5G high frequencies.